Thanks for coming. Let's get started. You had your midterm, and I looked at the grades, of course, and they looked really, really good to me. I was very much astonished. I was actually talking to Michelle Gabour. What happened? Why are they so good? Because your average grades were significantly better than they were in the so maybe that's just because I would have Michelle some great A's, or it is because you were just so smart. I don't know what it is, but something certainly better is going on this year than previous years, and I'm very happy about it. So you returned your practice midterm. As a reminder again, the midterm is Wednesday after President's Day. That is almost 2 weeks, not quite 2 weeks from now. So by that time we should have finished with statistical mechanics, and it should be at or near the break between statistical mechanics and kinetics. In addition, today there will be a homework which I'm going to assign you, and that homework will be due on Monday. That's an exception. Usually the homeworks are not due on Monday. This week it is, and the homework today will be just to keep on doing with the Excel file what I've been doing so far, and then submit the new version of that by Monday class, the first TAs. Okay, with that, we looked at the canonical partition function of things like this last time, and it's really important to get a feeling for what these functions are doing, because otherwise statistical mechanics appears to make no sense whatsoever. So we need to get a feeling of what those functions are doing. And so let us look back, look last time at Z, the canonical partition function of this particular molecule. And I'm using in my class the easier molecule which has no fluorine. You have the molecule with the one fluorine in there. And that will be the one which you do for homework again. But for that molecule, for just a quadriphenyl, if we look at Z, what we are seeing over here is that we have low temperature. The canonical partition function of that is 1. Why is the canonical partition function of the molecule at low temperatures 1? It is 1 because at low temperatures, it is the probability that the molecule will reside in only one state. So the canonical partition function sums up over all the states the molecule is in, weighed by this probability kind of thing. If the probability is such that the molecule can only reside in one state, then the canonical partition function just sums over one state. So it's really just 1, which is exactly what we're seeing. It's just 1 at low temperature. Just like when I gave you that homework for what's the canonical partition function of rolling a dice, and I look at the final state, there's 6 equivalent final states if you didn't load your dice in beforehand. They are all the same in energy for that. And as a consequence, then the canonical partition function at low temperature for your dice is 6. So it's just the number of states. Your canonical partition function, nothing else. But if then the states have different energy, then the summing up becomes a little bit more complicated. The summing up gets this weighing factor in there. The summing up will have this. It's not just the sum where you have 1 for each state, you have this e to the power of ej over kt in there. It is also something which then weighs in your summing with that e function. And if your energy for the state is large compared to kt, then that state will probably not be occupied and it doesn't really enter. It's a very small number only. And those states are being disregarded. So we can see actually that at 40 millielectron volts, at 40 millielectron volts for getting into the first excited state, we need to wait at maybe 100 Kelvin or so before something happens here in Z. We need to wait for the probability to change up to maybe 100 Kelvin or so, somewhere here, 100 Kelvin or so, where it starts that other states become relevant as well. So the energy of the state is related to at which temperature can be populated and at which temperature will play a role in Z. And as everything else depends on Z in statistical mechanics, then we'll see also that things like the probability will change there, things like the internal energy will change there, and many other aspects which we are going to know. So, statistical mechanics, we started out from this equipartition principle. Every state has the same probability to be filled. But that only holds if we have the same energy for the states. If we have different energies for the state, then we have different probabilities, and they all depend on the energy of the state divided by kT, or in units, if you wish, of kT. If kT is a large number, mainly because temperature is large, then we divide the energy by a large number, and it will be small, effectively, what comes out of it. At high energies, we can have even at high temperatures, we can even have high energy states populated, but otherwise we don't. Okay, next thing, what I mentioned last time is that we wanted to look at the entropy. And in order to look at the entropy, we first need to look at the pressure, because otherwise we can't get to the entropy. So, the first thing is we need to look at what is the pressure. And that's something I actually have to do on the board. That's obviously not your homework. So, let's get back over here. And you see, I forgot my notebook. I hope I can do it even. So, if I'm interested in what is the pressure of my system, then I'll do exactly the same thing. The pressure of my system is the average in some way of the pressures which I all have in the states Ej, right? That's just the same way. And so my pressure is really the sum over I, or sum over J, of all the probabilities Pj for having the pressure Pj. Same thing as I have over here. This was probability, it's energy here. If I'm interested in the internal energy, if I'm interested in the pressure, then it's the pressure, right? Now, if I'm interested in what is the pressure, then I really need to look at the first derivative of the energy of my system by the volume, that is minus the pressure. So, what I really need to do is I need to figure out what my first derivatives are. So that is then the first derivative of E to the power of minus E J over KT by the volume of the system, and I need to put the negative sign in front of it because it's minus T. Okay. And then, of course, I still have this normalization factor down here, which is the sum over I e to the power of minus EI over KT. Now, if I were to do this kind of calculation, then I can have a look at what is this one here. Now, if I do this, the K, and K is a number, T is a constant. If I'm going with regards to the volume, correct? So, what I really only can do my first derivative of is this EJ over here. So, I have my external first derivative, which gives me my EJ, e to the power of minus EJ over KT, which just reproduces the E function. Then I have this constant factor minus 1 over KT, which is just a number. And then I have the first derivative of the energy J by the volume, and then I still have my minus sign from over here, which cancels this minus sign. This is not an exponent, so this should have been down here on this one. It's not. And then it is, of course, the whole thing divided by sum over I e to the power of minus the I over KT. Okay. And then you can, of course, do the same thing. Then you can ask yourself, what is dz by dv? And if you ask yourself, what is dz by dv, you will find that you get almost the same thing as you have over here, except for this KT factor. So you'll come to the conclusion that you have need to cancel out the KT factor in order to get the pressure. You have KT times z by dv times 1 over z. Just the same way you get to that problem when you did it for internal energy. But here we can do the same thing then to say, oh, 1 over z by t is kt dl z by dv. So when we divide what is the pressure of our system, we get the same kind of formula as we got for the internal energy, with the only difference in the derivation being that when we took our first derivative by the temperature, which we needed to do up here, then we got kt square out of it, and for the pressure, we had the first derivative by the energy, so we never got the square over here. And so we have the T over here, and here we have the T squared. But otherwise, it's just the same thing. Okay. Now, knowing what the pressure is, knowing that we get the pressure the same way as we did it in before, we can try to attempt to describe what the entropy is. And there comes the interesting part. Because if I want to figure out what the entropy is, I start out du, the first total differential of the internal energy of the other system, is T ds minus P dv. And that's why we need to know what P is. And then we can rearrange that we get a formula for ds over there. If I rearrange it for ts, I have T ds equals du minus P dv, or ds equals 1 over T du minus P over T dv. Okay. Now how can I integrate that? It's still not kind of straightforward because this is a du and this is a dv. We can't really do separation of the variables. But we can wonder, what is this u and 1 over t kind of thing? What we can ask ourselves is, what would be a d of u over t? Now, what would that be? Now, this d of u over t, we can do two different, it's a total differential, which we have to look at over here. And so we can, let's say that this is first derivative by du, it's 1 over t times the du plus, now we have to look at the other variable in here, which is the t, and if I took the first derivative by t, it gives me a minus sign, so minus 1 over t squared the u, of course, is still there, dt. Okay. Now, this here, this 1 over t du, is the 1 over t du, which we have here. So, ds is d of u over t, and we put this in here, and there was a minus sign, so if I put it over to the other side, it's a plus sign, 1 over t squared u dt, and then we have the minus p over t dv. And the trick which you apply now is that you see, we have, for our ds, d over u over t plus 1 over t squared, and u is kt squared, kt squared dln z by dt dt. This dt here being that dt, this one here comes from the u. And here for the pressure we had minus, and we have kt over there, kt, and here we have 1 over t, and then we have dln z by dv. Now, this one here is then ds is d of u over t, d of u over t, and then k times dln z by dt dt minus dln z dv dv. That is a total differential of ln z. So I really have here d over u over t plus k times d of ln z, the total differential of ln z. And now I have a constant, and everywhere a differential of something. So now I can just forget about the d's, I can integrate the whole thing and say S equals u over t plus k times ln z plus an integration constant. And that integration constant is usually forgotten. So people don't have. And that is what we have over here. So just by doing this calculus, if you wish, and plugging in the formula for the pressure and plugging in the formula for the internal energy, we can get a formula for the entropy. Now, if we have a formula for the entropy based on the internal energy and the canonical partition function, that is something new, because thermodynamics could not tell us what really is the entropy. That only comes now out of statistical mechanics. Let us assume, for instance, a really simple case. Again, let us assume the die which we wrote. When we wrote our die and it's lying on the table, we said all the states of the die have the same energy, and it's reasonable to call that energy zero, because that's the ground state energy. Then the energy of the die, the internal energy, also needs to be zero. If it can only sit in different states in which always the energy is zero, then the average of that energy will also be zero, and so it will be zero. And then I have k, and then you know already what the canonical partition function of your die is. Canonical partition function of your die was 6, ln 6. So, if you have a system in which all states have the same energy, you can reasonably call that energy zero, and then the entropy is just k times the logarithm times the number of states you have in your system. And that is something you probably all knew in a way. You've heard about it, but it's something you can't get out of thermodynamics. There's no way thermodynamics can give you access to the microstates and can give you access to a formula which allows you to calculate what the entropy is. But in statistical mechanics, you know how to set up a z. We've done that on the computer all the time. We've set up a z. And it was used. But we've set up a z. Up there it is. And from that z, we can calculate what the internal energy is. And if that internal energy is zero, this term here on the left-hand side will be irrelevant. And then from the z, we directly get entropy. If the internal energy is not zero, then this is still only a function of the canonical partition function. Because the u over here is kt squared d ln z by dt. So if we know our canonical partition function, then we have a direct entropy meter in a way. And that is something which was historically absolutely missing for a good understanding of what that thing entropy is. And now entropy becomes something like really derivable. From our system, we can immediately derive our entropy. So let's do that. So if I'm interested in the entropy, then what would be the entropy for our system? It is, as I write over here, u over t. If I have u over t, I have u, and I have to divide that by the temperature, and the temperature was here, u over t. And then I need to add the Boltzmann times the logarithm of z. Comes in handy that we calculated all the values already. We calculated the C already, we calculated the U already. There's nothing new over here, so it's really easy to calculate what the entropy is. And I think the entropy, I can just pull it over straight to the side. And then I can say, okay, I want to insert a graph. I have entropy, and the x-axis is temperature, and the y-axis is entropy. And get my graph. So I have my entropy. What you see is all those curves look somewhat similar. They don't look identical, but they look somewhat similar going. So my entropy can be calculated right away. Our system. Now we can calculate entropy from looking at something. Next step, what I'm interested in is the heat capacity of my system. If I'm interested in the heat capacity of my system, can I also get that? Capacity and pressure, they're again very much the same thing. Because for the pressure, I was concerned in what is the first derivative of the energy by the volume. For the heat capacity, I'm interested in what is the first derivative of the system by temperature, of the energy of the system by temperature. So I have then something on the order of d by dt of the energy of my system, which was sum over j, e j times e to the power of minus ej over kt, and the whole thing divided by the canonical partition function, e to the power of minus ei over kt, and the first derivative of the temperature, so that I get my heat capacity. And in order to make the canonical ensemble, it cannot exchange volume with the outside world, otherwise we wouldn't have the same average of the system over time, and over systems is identical volume, and so it needs to be the capacity at constant volume. Okay, heat capacity at constant volume is the first derivative by the temperature of whatever is the energy of the system, and that is given over here. That again looks so familiar, doesn't it? We've done that already essentially once over, and now we're doing it again. So if I have to do this calculation here, that is the product, right? That's sum over j, ej over eta, and so on, times 1 over that. So I need to use my product or a quotient rule for making first derivatives. So if I'm doing this, then I'm getting over here, I can put my first derivative inside the sum. I'm getting here the first derivative by t. Ej doesn't depend on t, and then so I have some j, e, j, and now I'm getting my first derivative here. The first derivative is first the outside first derivative, e to the power of minus ej over kt. The e function doesn't change if I take the first derivative of it. And then the internal first derivative, where ej over k with a minus sign in front of it was a constant, and then the first derivative of 1 over t, which is minus 1 over t squared. And then conveniently those two minus signs cancel, and that needs to be divided by the sum over I, just this one, e to the power of minus ei over k t. Okay, but that was only doing the first derivative in the numerator. Now I need to take the first derivative in the denominator as well. And so for my product rule, I need to then say that is this one now stays unchanged. That is the sum over j e to the power of ej times e to the power of minus ej over k t. And then the first derivative of by t of what I have over there. So for that, the outsidemost first derivative is the one from 1 over this one here, which gives me a minus 1 over the sum over I e to the power of minus ei over kt, the whole thing squared. That is the first derivative from this one here was in the denominator. And then the first derivative internally over here is that I have to get is the e function, e to the power of minus ei over kt, well, the sum stays, the e function stays of that, and then the internal derivative of this one here takes out the minus ei over kt as a over k as a constant, and then it has still the first derivative from 1 over t, which is minus 1 over t squared. So that was my first derivative of this term by t. I'm sorry that this is so lengthy, but t is up here and t is down here, and so the first derivative is longish. But the good thing is we are essentially done at this point. Because what we see over here, this is on the left-hand side. This is 1 over kt squared, 1 over kt squared, the sum over ej squared times e to the power of minus ej over kt divided by the sum over I e to the power of minus ei over kt. And then on the right-hand side, we have 3 minus signs. There's a minus sign, there's a minus sign, there's a minus sign, so there's a whole minus sign in front of it. And then we have this sum over j, ej, ej times e to the power of minus ej over kt. And we have it once here, and we have it once here. There we have the same thing again. So it's this one here we squared, and then we have our 1 over kt still. So I'll put that here, 1 over kt squared, and then the whole thing is divided by the sum over I e to the power of minus ei over kt. And that whole thing here was squared as well. Okay, and we're done. Because
This is 1 over kt squared. I can take that out. We have it everywhere. 1 over kt squared. And now what I have here, that is the average for Ej squared, right? That was my average for Ej squared. If I want to know what is the average of Ej squared in my system, calculating the sum over j Ej squared times e to the power of minus Ej over kt divided by the canonical partition function is what I have to do. So that one here on the left-hand side is just the average for Ej squared in my system. And what I have on the right-hand side here was 1 over kt, which I put on the outside here, minus, and then I have a square over here. And so this one here, if I forget about the squares, then this one would be just the average for the energy, correct? And then I have the squares. So that is the average of the energy squared. Here's the square inside the average. Here's the square on the outside of the average. But that's it. That's the only difference. So if I ask myself, what is the heat capacity of a system? It is a factor, 1 over kt squared, times the difference between looking at the average of the square of the energy minus the square of the average of the energy. So we can immediately calculate what is our heat capacity in our system, because if I want to know what is Cv in the system, then for Cv, I need to have 1 over kt squared. I'll probably do that at the end, 1 over kt squared. I have this divided up. So, and I have my Ej, the average of the Ej. What is that? The average of the Ej, what that is, we actually saw right before here. We saw what that is over here. That is the sum of Ej times Ej times e to the power of minus Ej. So that's the sum product clearly, and it is the sum product of the e to the power of minus Ej over kt terms and the energy Ej and the energy Ej again. It is the energy Ej times the energy Ej times the e to the power of minus Ej over kt. And the whole thing needs to be divided by z. Needs to be divided by z over here. This is z. Now we know what z is, we calculated that. So we can divide it by z. And from that, we need to subtract what the energy of our system is squared. Now the energy of our system was U, correct? So the energy of our system was U. And in times U, that is the energy of our system squared. And then I can close the parenthesis. And I still need to divide, because I didn't do it in the beginning, I still need to divide by K Boltzmann. And the temperature squared. that division is equal to KT squared.
Okay. So, I have the heat capacity of my system right away. I want to pull it over to the side now, the heat capacity of the system, but that would not work at the moment because I still need to protect some fields to do that. If I do it just the stupid way, this way, then I would move this here over to the side. I don't want to have the red fields moved to the side. I want them to stay there. So before I do this here, I need to make sure that when I'm referring to the energy, the column is protected, and so my D's need to be protected. Now, then I think nothing, it all stays nicely in the column, so that works okay. So I can put it all the way to the side. And then I can insert yet another graph, and in this other graph, I select data, and I'm interested now heat capacity, CV, and the X values are temperatures which I have over here, and the Y values are the heat capacity and like this. So, the question then might be, why does this plot look so much different than the other ones? Let's have a look at this. Why does this look different? Okay, that's what we just got. Let's first see whether we can understand our heat. Heat capacity is low at low temperatures. That makes sense because over here, the heat capacity, there's no change in energy if we warm up our system. So the heat capacity is really low, or there's barely a change of internal energy if we warm up our system. Why is that the case? Because the first excited state, having one set of coplanar rings, costs a lot of energy. And at those very low temperatures which we have over here, we just don't have the thermal energy to make that happen. It's very unlikely that there is enough thermal energy available to even form one coplanar ring pair. And so there's really nothing happening. The system just stays in the ground state. And because the system just stays in the ground state, very little energy is put in the system when I warm it up. And as a consequence, the heat capacity is really low because warming it up just a little bit doesn't make a big energy difference anyway. And then we'll get to the temperatures where we get a big change in probability. And we see that at this place, we are getting kind of the maximum slope of our internal energy. Here, we are able to put energy in our system. And the heat capacity goes up to this value of 1.4% times 10 to the minus 23rd. That goes up to pretty much that value. So we are getting a heat capacity in our system of about K. It is just the Boltzmann constant. So this 1.38 times 10 to the minus 23, this is pretty precisely the maximum of our heat capacity. So even though that is a completely phony made-up system, which I showed you,
it will show approximately K as the heat capacity. And that is then the maximum slope which I have. And then the system becomes even more phony, because at some point, if we are in the temperatures above this peak over here, if we are then going down on the side, if we are above like 300 Kelvin or so, then we pop above 300 Kelvin, we are here or so, then the system would be happy to occupy also a state with even higher energy, a state which has not 0 or 1 or 2 or 3, but maybe 4 or 5 or 6 copanoids. But of course there is no such state for that molecule, because you only have 4 rings in total in that molecule. And so it can't populate that. There is no high energy state for that system anymore available. And as a consequence, if there's no high energy state available anymore, then we can't put the heat in our system which we could otherwise put in. And C cannot stay up here anymore, because we already filled all the energetic states, and the heat capacity is going down of our system again. That is mostly not the case in reality. Usually in reality, there are always more and higher energy states available. It's not a finite number of states, like maximum is 4 in the system, and the heat capacity in most realistic systems might plateau, but will not go down. But then this was a very, very simple molecule, a very simple system to investigate. And what we then find is that when the heat capacity is going down, and as a consequence, the energy is not climbing very much anymore when we go to high temperatures. It's easy to heat the molecule farther, because you don't need to put in so much heat anymore. We are also approximating here very similar probabilities of all the states. So if our temperature is high enough, then we are getting back to close to the equipartition principle, that we have the same probability for all states. It's not exactly the same over here, but it's not orders of magnitude in between as they were over here. They are getting already close over here. If I were to go to slightly higher temperatures, and then I would do that. So if I were to look at, not start at 10 Kelvin over here, but rather maybe I started at 25 Kelvins over here in my system, then you'll see that we get to much higher temperatures over here, 3,500, and then we really get close to that equipartition principle. Then it is also easy to lose the small peak here in the heat capacity. It's only in a very narrow area, and if you're looking over the whole region, you have a different system. So I'll put that back so that we can see it. Maybe I should go to low temperature regime here for a moment and say, okay, if I start at maybe 4 or so Kelvin in my system. If I start at 4 Kelvin in my system, then it looks okay, the heat capacity is going up, can do it even smaller, starting value with 2 Kelvin, starting at 2 Kelvin, then almost over the whole range here, I can see a very nice kind of straight heat capacity. What you like from heat capacity is a straight line that is constant here. Over a fairly large range, we have over here, heat capacity is constant, correct? That's what we want from heat capacities. So in reality, in the world we are living, we are in this particular regime where the heat capacity is constant in many systems. But that only, where that regime is, depends on how much is the energy spacing of the state. So if I have 40 millielectron volts, it would be at about 100 Kelvin. If my energy of the system would be a little bit larger, if my energetic spacing of the system had rather been 60 millielectron volts or so, then I could have gotten to a state where we are closer to room temperature, and then you could play with that more and more and see what would be the energy spacing of the states of your system so that I get the desirable kind of flat and constant heat capacity of the system. Okay, all those kind of things can be analyzed in this way of setting things up. Please reproduce up to here the same table I have here. You don't need to do the derivation which I have on the board. Don't do that, but look at the results of it. And then on next week we are going to look at the gas, at a diatomic gas, and see the heat capacity and other properties of that one is based on statistical mechanics. Okay.